Hello everybody and welcome back to another video. Today I am going to introduce to you the method of integration by substitution. In the integration by substitution, you are looking for an expression within the integrand whose derivative up to a constant factor also appears in the integrand. This expression is replaced by a new variable. As a result, the integrand can be simplified since the substituted expression and its differential simplify, leading to a much simpler integral. I will go for a couple of examples, and you are welcome to pause the video at any time for detecting the correct term to substitute. First, I will do some indefinite integrals, so you get the principle. And afterwards, I will do one or two examples for an indefinite integral because there's a little clue to it with regard to the limits of the integral. Without further ado, we dive right into the first example. So we are looking for the integral of x multiplied by x to the power of x squared dx. All right. So, to remember, you are looking for an expression within the integrand whose derivative up to a constant factor also appears in the integrand. Now take a look at our integrand here. You have two factors. You have x and you have e to the power of x squared. Now, if you differentiate x, it'll become 1, it's obvious. If you differentiate x to the power of 2, it will become 2x. And 2x appears in this integrand apart from a constant factor. It's x. Okay, so you are going to substitute x to the power of 2. So we are going to do that. Our substitutional variable, let's call it z. We substitute x squared. Okay, so now we differentiate. We write dz dx is equal to 2x. All right, and now we multiply with dx and we have dz is equal to 2x dx. Okay, so what's the point you're thinking? Take a look. We have this expression here, x times dx, and it appears also in our integral. Here is x and here is dx. So what we now do is we divide by 2, and then we have 1/2 dz is equal to x dx. So what we now can do is we look for x dx, which is here to be found, and we replace it. We replace it with this term. On top, we substitute x squared with that. All right, so we go from this integral. After the substitution, the integral looks the following. So I'll write it the other way so it gets a little bit more clear. Dx. Okay, I just switched the places so that you can see a little bit clearer. We have here x dx, and this is equal to 1/2 dz. Now we go for the substitution. We have e, we substitute x to the power of 2 for z. Okay, so we have e to the power of z, and now we have x times dx which is after substitution 1.5 dz, or not 1.5, a half dz, so 0.5 dz. Okay, this is our new integral. Now we can simplify it. 1.5 to e to the power of z dz. Now we'll see, we will reckon that this integral is very easy to solve because it comes out to 1.5 e to the power of z plus c. Okay, so obviously this function is the stem function of 1.5 of a half e to the power of z. And now what we are now going to do is, in the next step, we back substitute. We back substitute our z so that our stem function is equal to 1.5 e to the power, we substituted, z is x squared plus c, and we are ready. We can do a test. So if we differentiate this function, we should get this function. So we do that to see if everything works out right. We have 2x divided by 2 e to the power of x squared is equal to x e x squared. So our integration was successful. Okay, once again, I go through it a little, I'll explain it one more time. So you have a function. You have found an expression within the integrand whose derivative also appears in the integrand. So we found x squared. If you differentiate x squared is 2x, so x appears in the integrand. So we substitute x squared through z. So you define z to be x to the power of 2. Then to differentiate this function, which is 2x, you multiply by dx, and now you put this side of the equation in the form that you directly find what you can substitute here. So we have x times dx, we have x times dx, so we divide by 2, so we have 1.5 dz is equal to x times dx, and we have x times dx, and that's exactly what we substitute. So we have, first of all, the substitution of x to the power of 2, which in this step is z, e to the power of z, e to the power of z, and then we substitute x times dx with 1.5 dz. This is this here. So we substituted x times dx with 1.5 dz, and we substituted x to the power of 2 with z. And after a little bit of simplification, this integral is very easy to solve, obviously. And this is our stem function. But take a look, our variable in the stem function is z. Okay, so for the final solution, you need to back substitute your stem function with z. Just take a look at the beginning of the task. Just at the beginning, z is x to the power of 2, and now you resubstitute z with the x to the power of 2, and you are done. Next integral is sine x multiplied by cosine x dx. This function, the first function, this would be possible to solve by integration by parts. My first video, I explained it in my first video. This function you would be able to solve via integration by parts. However, this function, you would not be able to solve via integration by parts because none of the factors disappears after one or more differentiations. So you have to choose integration by substitution. All right, so we are looking for, once again, we are looking for an expression within the integrand whose derivative also appears in the integrand. In this case, the derivative of sine x is cosine x, so that's great. But the derivative of cosine x is minus sine x. So in this case, it doesn't really matter which factor you choose to substitute. We will check for both scenarios just to see. First, we substitute sine x. Okay, as you remember, we go for the derivative. dz dx is equal to cosine x. And now we multiply dx, so we have dz is equal to cosine x dx. I see cosine x dx is to be substituted with dz, and sine x is to be substituted with z. Right? So we have the integral of z multiplied by dz. This integral, you would agree, is very easy. Okay, so we first, once again, I go through the steps. First of all, we choose a factor to substitute. In this case, sine x. We differentiated sine x, and we solved this expression for dz. And we put that, substitute it in there. So we just have to solve this integral, which is obviously 1.5 squared plus c. Okay. So now you back substitute. Our initial integral was sine x multiplied by cosine x dx, which is equal to 1.5. Back substitute. So z is equal to sine x sine x squared plus c. So we do the test, we just differentiate, and you'll see you got the outer derivative multiplied by the inner derivative, which is 2.5 sine x to the power of 1 multiplied by cosine x, which is sine x multiplied by cosine x, which is what we started with. Now we go for another example. The next example is going to be 2x divided by 1 plus x squared dx. Again, you're looking for what to substitute. If you take a look, if you differentiate 2x, you get x, which appears here. So you can substitute the whole term is 1 plus x squared dz dx is equal to 2x, and dz is equal to 2x multiplied by dx. And you see 2x dx appears in our integrand. So as our new substituted integrand, we have 1 divided by z multiplied by dz. Because, again, dz is equal to 2x times dx. It's this term, 2x times dx. And we substituted 1 plus x squared with z. So this is our new integral. Doesn't look too fancy, does it? So we can easily solve this. It's a logarithmus naturalis plus c. And now, again, back substitute. So yeah, our stem function is equal to logarithmus naturalis 1 plus x squared plus c. Very easy, just basically 2 lines. We check. Is equal to, we have our inner function, the differentiation of the inner function multiplied by the differentiation of the outer function. We have 2x divided by 1 plus x squared. And you see the integration was successful. So the next function is 1 divided by x multiplied logarithmus naturalis x dx. So it's a little bit more complicated. The thing is, if you're not too sure about what to substitute, the process of substitution, as you have seen, is not too, you usually don't spend too much time. Okay, so basically it's just 3 or 4 lines. So if you get to the point where you see, okay, maybe I should substitute something else because it doesn't work, you can do it. Usually, if you practice and you see what you're looking for, these integration by substitution questions in the exam, usually if you develop an eye for this kind of integration, you will solve these tasks within, I don't know, 1 or 2 minutes. Yeah, maybe 3, 4. This is very fast and very easy points if you know what you're doing. Okay, so let's see what we substitute. So if we differentiate ln x, it's 1 divided by x. This doesn't look too bad. If we differentiate x, it's 1. So I would go for ln x is to substitute. Differentiate is multiple of x, and we have dz is equal to x dx. Now we can write this, or maybe let's say we can is equal to x dx is the same. So after substitution, we have the integral of 1 over z dz. Again, we substituted ln the logarithmus naturalis of x with z, it's this term, this term, and dz is equal to 1 divided by x multiplied dx. That's this and this term. Okay, substituted ln x with z, and 1 divided by x multiplied by dx has become dz. Okay, that's not complicated. So we have logarithmus naturalis z plus c. Now we back substitute again. Back substitute, and we have our stamp function is equal to the logarithmus naturalis. What did we substitute? ln x. ln x plus c. So it's like a double logarithmus naturalis. You take the logarithmus naturalis from x, and afterwards you take the logarithmus naturalis from ln x. Okay, we check. So we have the inner derivative. ln x is 1 divided by x multiplied by the outer derivative, which is this function, which is 1 divided by ln x, which comes out to 1 divided by x ln x, which is equal to our starting function. Okay, so these examples all have been indefinite integrals. You see, if you do this, if you try to go on your own, solve these examples on your own, you get a feeling for that. You get a feeling for it quite easily, I guess, and if you know what you have to look for, and you get used to the substitutions, maybe you're going to have fun with it, maybe. All right, and now I am going for an example referring to a definite integral. Okay, so we have an integral with upper and lower limits. There's a little thing you have to be aware of when you apply this method to integrals with limits, but if you know the trick, it's not hard by any means. So now I'm going to show you to apply the method to a definite integral. For that, we have the integral from 0 to p half of sine x multiplied by cosine x dx. Okay, first step is the same. We choose which factor to substitute. The easiest is, in this case, it doesn't matter. The easiest, a little bit easier, is sine x. Sine x dx is equal to cosine x. So dz is equal to cosine x dx. So put that in. Substituted sine x with z. Cosine x dx is equal to dz multiplied by dz. Okay, it's our substitution. Now, we do have to deal with the limits. And there are two ways to handle them. I will show you both. The first way is to put in your upper and lower limit into this z function. Put it in. So you do have, as you get new limits after the substitution, your upper limit, so you put p half into this function. So your new upper limit is sine p half, and your new lower limit is sine of 0. Again, if you have your substituted integral, you put in your limits from the non-substituted function, and these limits put into your substitution function. And these are your new limits, so sine of p half and sine of 0. So this integral is not too easy to solve as well, so this is 1.5 z squared in from sine 0 to p half, which comes out to, which is equal to 1.5 z squared p half 0, which is equal to 1.5. So you get 1.5. So the integral, this definite integral, comes out to 1.5. This is method number 1 to do it. There is a second one. I will show you this as well, because sometimes to put this term into the upper and lower limits can be a little bit tricky. It depends on the function. So you have another option. You have the integral of z dz. Now you have your stem function, which is 1.5 z squared, which is 1 divided by 2 z squared. And now you back substitute, and you have 1.5 multiplied by sine x squared. Okay, this is your stem function. And now you can put in your original limits again, because you back substituted. This has been half and 0, and this comes out to, you can check it if you want, but you can trust me as well. This is 1.5 as well. So again, you have the two options for a definite integral. You do the method of integration by substitution all the way, and on this step, okay, if you're going for the integral referring to z, you put in new limits. Okay, you take your old limits, put them into your substitution, and these become your new limits. This is step 1. Therefore, you don't have to back substitute. You can just solve the integral with your substitution, which you see is quite easy as well. The second step, if you're like unsure, maybe this is pretty complicated, you first back substitute. Okay, look for what was your z. Z was sine x. You put in, and then you back substitute it, and then you can put in your original limits. You see, it doesn't matter how you proceed. Maybe your teacher prefers one or the other, and then you do it, but basically it comes out. The trick is to substitute the limits as well, if you stick to option number 1. All right. So I will go for another example. This will be the last, and it's going to be a little bit more complicated, but yeah, referring to the function is not amazingly horrible. We're looking for the definite integral. 0 x divided by the square root of 1 minus x squared dx. Again, first step, identifying what to substitute. And you see this term, if you differentiate it, you get something like minus 2x, and minus 2 is just a constant factor, so you can go for the whole term with the square root. So z is equal to the square root of 1 minus x squared. It's a lot easier if you write roots as exponents. It's just an I thing. Yeah, it just looks less scary. All right, so we differentiate, which is the differentiation of the inner function multiplied by the differentiation of the outer function, which comes out to minus 2x multiplied by 1.5 multiplied divided by 1.5 multiplied by 1 minus x to the power 2 of minus 1.5, which is equal to minus 2x divided by 2 multiplied by the square root of 1 minus x squared. I can shorten the fraction and solve for dz, which will leave you with dz is equal to minus x divided by the square root of 1 minus x squared multiplied with the dx. Now you multiply by minus 1, you have minus dz is equal to x divided by 1 minus x squared dx. Now you see this term is exactly this term. It's the exact same. We get the integral of minus dz with the limits of, okay, your limits have to be put in here. So you have your new limits. Yeah, you have your new limits. 1 minus 1.5 squared to the power squared to the power of 1.5 divided by 1 minus 0 squared 1.5. Okay, this is equal to minus the integral dz, which is equal to minus the integral of z. And then this comes out to roughly 0.134. All right. This was the first option, where you put in your limits. You put your limits into your substitutional function, the function you substituted. Second option is the resubstitution. First, resubstitute. So you have minus the integral dz, which is equal to minus the integral of z. Which is equal to minus. Now you resubstitute the process of, now you resubstitute, so you have minus 1 minus x squared, 1 minus half. You put in and now you put in the original borders, 0 and half, and that comes out 1.5, 0, which comes out to the same 0.134. Okay, so we have the two methods. Method 1 is with no resubstitution, but you have to substitute your limits, and after resubstitution, your z was this term. You don't have. You can take your original limits to put in, and that's it. As always, I hope you've taken something out of it. So I hope you don't have to be afraid of integration by substitution anymore.